P2P engineering field. Nice to meet you all again in this amazing Saturday, 19 December 2020. As usual, before we start our program, we would like to inform you the protocol during the video conference. Please listen it carefully. The first, please kindly adjust your name or ID screen using the format your university or your institutions underscore your name. Second, during the video conference, we kindly ask all participants to turn off the audio and only turn on the audio when Master of Ceremony, speaker, or moderator give the order. The third, we would like to recommend all participants to adjust the seat positions comfortably and prevent the backlight effect. The fourth, please ensure your network has a stable internet connections for your convenience during the event. Last but not least, we recommend all participants to use a headset or earphones for clear and better sound.
Ms. Bilkis, your voice is not too clear. Your voice is too soft. Yeah. Could you please speak louder, Ms. Bilkis?
Okay, how about now, Ibu Maria?
A bit better, but maybe you can set up louder a bit.
Okay.
Yes, that's fine. This one.
Okay, thank you so much, Dr. Maria. We also encourage for all participants of 12 series of virtual public lecture P2P to fill in the form attendance on the link that will be shared by the committee in the chat box. Committee, could you please help me to share the attendance link to the chat box? Okay, we are about to open our event. Okay, Assalamualaikum warahmatullahi wabarakatuh. Best wishes to us all. We thank God Almighty because over the blessings and graces we can gather at our event today. A warm welcome to all of you in the 12th series of virtual public lecture of P2P, people-to-people relationships in engineering field, a joint program that held between the Educational and Culture Task of Indonesia's Embassy in Washington, D.C., USA, MRPTNI, Majelis Rektor Perguruan Tinggi Negeri Indonesia, and I4, Ikatan Ilmuwan Indonesia International, USA, and Canada, in this amazing Saturday, 19 December 2020. Ladies and gentlemen, please allow me to greet the Honorable Professor Anastasia Muliana from Texas A&M University as our speaker today. The Honorable Dr. Latifah Nur Rahmi as our moderator for our virtual public lecture today, and all participants of virtual public lecture P2P Engineering Field 2020 from Sabang until Merauke. Just glimpse information about 50L P2P engineering field. We have engaged more than 6,000 participants within series 1 and 11 of 50L P2P from all over Indonesia. And our meeting today is 12 series of 50L P2P, and this is the last series of 50L P2P. But we still encourage all of you to share this event link to anyone who is interested about the topic, or everyone also can watch in our official YouTube channel in ITS International's office. Ladies and gentlemen, however, it's not about the number, but the impact that must be spread to all people, because we believe start from here, we can do something for our beloved country, Indonesia. Before we proceed to our main event today, please allow me to once again remind you to fill in the attendance form so that we could share the materials to all of you after this event ends. And for your information, 50L P2P is no longer provide the participant with the e-certificate, and we will replace it by material disseminations competitions for 50L P2P engineering field participants. Later on, we will inform you on exciting material disseminations competitions for 50L P2P engineering field. Additional information, all participants' microphone will be muted and could only unmuted by approval of committee. You can use raise hand features so that we could unmute you during the Q&A sessions, And we will also provide you with the Google Forms link with the Q&A sessions. Okay, without any further ado, I would like to invite and introduce you to our moderators for today's event. Okay, today's event we have Dr. Latifa Nurrahmi. Dr. Latifa is a lecturer and researcher at ITS Mechanical Engineering Department. Her educational background is mechanical engineering from Institut Teknologi 10 November, Surabaya, Indonesia, and for a master degree from Design of Systems and Products, École Centrale de Nantes, France, and for the doctor's degree is from École Centrale de Nantes, France as well. For the research interest is design of mechanism, kinematics, dynamics, reconfigurable manipulators, parallel manipulators, cable-driven parallel robots, and type synthesis. For her activities, she is assistant professor at Department of Mechanical Engineering ITS, head of Industrial Robotics Center of Excellence of Mechatronics and Industrial Automations ITS, and head of Laboratory of Control and System Engineering at the Department of Mechanical Engineering ITS. She also has so many grants and awards from our government and also internationally. So that's for Dr. Latifa curriculum vitae. So she is the amazing woman that will guide us during the virtual public lecture with Professor Anastasia Muliana today. Hello, Dr. Latifa. How are you?
Hello, Mbak Bilkis. Fine, thank you.
Wow, that's so great. Are you excited for today, Dr. Latifa?
Very excited.
The same way. Okay, Dr. Latifa, I'm officially give the microphone to you, and time and place is yours.
Thank you, Mbak Bilkis. Hello, everyone. Good morning. I hope you all are in a good shape this morning, wherever you are, at home or in campus. And welcome again to today's last series of P2P virtual public lecture in engineering field. I'm glad to be your moderators for today's lecture. And first of all, let me say hello and good evening to Professor Anastasia. How are you?
Good morning there. Thank you for inviting me.
Right, good evening there, and good morning to Pak Irfan, Bu Maria. Good evening to Professor George Anwar, who is currently coming to this morning lecture. Thank you very much. And before coming to the main lecture, allow me to introduce our speaker and read the biography. Our speaker today, her name is Professor Anastasia Muliana. She finished her bachelor degree from ITB, Indonesia, and she obtained her master and PhD degree from Georgia Institute of Technology from the United States. She is currently a professor in the Department of Mechanical Engineering, Texas A&M University, United States. Her research interests include modeling and simulation of nonlinear and time-dependent response of materials and structures under multiple stimuli, mechanical in terms of mechanical, thermal, chemical, electrical, and lights. This includes as well viscoelastic modeling of polymers, composites, active materials, and plant stems. Long-term degradation and life prediction of polymers and composites, and stimulations of deformations in adaptive and flexible structures with applications in stents. As I told you before, she's currently a professor at the Department of Mechanical Engineering, Texas A&M University in the United States. And she's also research associate in National Energy Technology Lab, West
No,
Virginia.
sorry, can I interrupt? This is not correct. I'm not affiliated with any national energy technology.
Okay, I'm sorry then.
Yeah, so there might be a mistake somewhere there.
My apology.
No problem.
And she is a recipient of National Science Foundation Career Award. I hope this is correct.
Yes.
Office of Scientific Research, YIP Award, US Presidential Early Career Award for scientists and engineers. I believe she has quite extensive experience and awards, and also William Keeler Memorial Award, and among others. She's a fellow of the American Society of Mechanical Engineers, ASME. I would like to remind you again that the lecture this morning will be about 50 up to 60 minutes. And after that, we'll continue with a question and answer session for about 30 minutes. You may ask the audience here, the participants, you may ask in Indonesia. It doesn't matter. And you can also ask in English. You can type your questions in the form that has been shared in the chat group in Zoom this morning, or you can also raise hand so that you can talk directly to the speaker this morning. All right, without further ado, I'd like to welcome our speaker. The floor is yours, Professor Anastasia.
All right, thank you very much. So let me share screen. Okay, so good morning, everyone. So first, I would like to thank the committee and the organizer, for making this virtual public lecture series happen. This has been a great opportunities for us to learn about each other work, and hopefully in the future we can start collaborating. So I would like to also thank all the participants who make an effort in joining this lecture. I hope you would learn something or at least have fun with this presentation. So what I'm going to talk today is actually more or less about my research on the mechanics of polymer and soft material. So I'll share a little bit background about this polymer and soft material, and what excites me also with the knowledge or the study that we actually did on polymer and soft material is open so many opportunities for collaboration across different disciplines. So this will actually bring like a new knowledge for my side, and what also a nice thing is that I could also contribute, to work with a colleague across different disciplines. So just to try or learn about all this exciting research or field out there. Right. So now before I start, I just want to briefly introduce about Texas A&M if some of you might not heard about it. So we are actually in state of Texas, right? So the location is in College Station. It's a college town situated in between Houston and Austin. So it's about 90 miles away from each city. So if you look at by number, so we are actually pretty old, relatively. Okay, so it's founded in 1876, and the population of students is actually quite large, so more than 69,000. So this also include our branch campuses in Qatar, and also several in the Texas area. So now we are, for the College of Engineering, so we are actually about 1/3 of the total population of Texas A&M, with like a 650 faculty split among like a 14 departments. So where I'm from is actually mechanical engineering. So we have about 2,000 students, both undergrad and graduate student, and 63 core faculty. So that's just a bit background about Texas A&M University. So now moving to actually what I'm doing. So my core expertise is in solid mechanics. specifically, we work a lot with a polymer and soft material, looking at the response and performance under various stimuli. That would include mechanical, thermal, electric, and so on, right? So the exciting thing about the polymer is actually we can have a polymer with a wide range of property through the control and also polymer blending. So of course, the wide range is still within a certain range, right? So now one thing also with the idea of this polymer, when we look at what make it exciting or unique, is because of this micromolecular arrangement. So when you look at the overall macroscopic response, we always see what we call nonlinear behavior and the time-dependent response. So now with all of this nature of the polymer, right? So it's open door to many other like research opportunities. So while I'm just only gonna give you like a several, I guess, example of research area where we can actually with the knowledge in polymer, we can contribute, but it's not limited to what I'm actually gonna share today. So, well, one of these applications, so we can also look at what we call a flexible and compliant system. So for example, this also include reconfigurable system of a different scale. So about 2 months ago, I present what we call a flexible facade. So this during, I think, architecture and urban planning virtual lecture. So you might also heard about this reconfigurable or morphing wing concept, but this is for like either micro air vehicle or down the roads in like a larger scale. But through this reconfigurable shape, so there is also the mechanism and also materials, right? So there are different materials that has been considered to achieve such a shape reconfigurable. Now with another area is like soft actuator or soft robotic. You might heard about this as well. So the body of the robot is made of like either elastomer or silicon elastomer. It can be actuated through mechanics like pneumatic, for example, or non-mechanical aspect, right? So this is just another example. Then moving to a smaller scale, so we also look at foldable or bilayer. So the idea about this is actually for microfabrication. When we try to fabricate a small scale system, it's quite difficult to achieve complex shape, right? So now by looking at like a different way, for example, with the bilayer system, like each layer has significantly different physical properties. Through the activation of non-mechanical stimuli, we can achieve various like a complex geometry. So that's one aspect of area that where polymer can come or play a role there. The other aspect is actually when we look at also biomechanics and bioengineering. So while the nature of this polymer, this is relatively soft, right? So depending, of course, on what kind of polymer we are talking about and also what kind of soft material. So with that knowledge, actually, we can also look at or study the response or mechanical response of tissues. You can also think of animal tissues or plant tissues, right? Just to give you an example. So this is a stem or a stalk of a grass crop. So this is a sorghum. So when an engineer see this, think about it like you have a bar or a cantilever bar anchored on the ground, right? So now when you look at the structure, this actually has a reinforcement. It's like an outer skin as like a stiff and strong enough. And inside we have a soft core. So this is like a composite system. So now if you look at in a smaller scale, this has like a cell wall. When you look at in closer loop, it's look like a honeycomb or lattice kind of structure. Well, this cell wall has actually fibers. It's a natural fiber like cellulose, hemicellulose, and lignin base. Now the basic building block of all this is actually polymer. So that's where when we know or have a knowledge in the mechanics of polymer, this would be exciting to also looking at what is the response of the biomechanics of plant tissues. So this is one area where actually we can study, and just to look at the response, like the influence or morphology and anatomy on the macroscopic mechanical response of this stem. Now, as for the bioengineering, there are a lot of application in polymer for implant, tissue scaffold, right? So I'm just gonna give you all these 2 examples. So it can be for like a bone implant or vascular stent, right? So the vascular stent, for example, there's been studied to use biodegradable stent. So this is for temporary implant. So now the other component, well, where we look at polymer. So recently with the advance in 3D printing, right? So make it possible for us to print or manufacture system with various complex geometry. So if you visit this website, I found it very interesting where this is through using the polymer, you can print like the actual size and also the geometry, right? Of like in this example is a human skull. It can be also other part or component with a complex, with a complex geometry. So, and another application of a polymer is actually when we look at larger scale structure. So this is an example of a Boeing Dreamliner, where a lot of components are made of polymer reinforced with fiber. It could be carbon fiber or glass fiber. So here I'm just showing you the scale where we look at the manufacturing. So the manufacturing of this composite actually involve high pressure and high temperature. So where we see all these phase transformation or phase change from liquid to maybe solidified polymer, right? So, well, when we have a knowledge in the mechanics of polymer, then we can jump in and try to understand or study the processing aspect of this polymer, and of course through the composite. So the other application, this may be many of you may be already familiar with energy dissipation. So either for vibration suppression or a lot of application in defense. So this is for like bulletproof or body armor, right? Again, this is a polymer composite. So you can have a fiber, for example, Kevlar fiber with a polymeric matrix with a certain design. So we can have a good energy dissipation mechanism. So this just several examples where the polymers are being applied. With my knowledge or my expertise in the mechanics of polymers, so there are many research opportunities where actually I can be part of. But of course, that's not just easily said, but it's not really easily done. So meaning we really need to communicate with experts in the field, and we really need to learn a lot about the problem in the field before we actually be able to work together with them. But what I'm trying to say here, it is just when we move out of our comfort zone, there are plenty of other exciting problems that we didn't even know before that actually we can be part of and contribute. So this is make the research is exciting, at least that's for me. So now moving on, so what exactly my contribution, so or our group has been working on. So we focus really on the theoretical and computational aspect, right? So we try to describe the time-dependent aspect of this polymer and soft material in general under exposure to mechanical and non-mechanical stimuli. What the expectation is, we want to have a digital model, so we can use this to predict the outcome or the response of the system of the structure prior to the design of the system. So the idea here, okay, we can really reduce the experimental trial and error process, right? So because if we don't have like an analysis or the tools to give you a better prediction, we tend to do experiment with trial and error. It can be time consuming and also could be costly. So with an informed model, we can maybe minimize or reduce that aspect, and hopefully we can also have the ability to better predict the response of the device that we are designing. So now to achieve all of this, there are just 3 components first we need a reliable material model. So here I'm working with composite. So one of the main thing with the, I'm working with polymer, including the composite. One of the main thing is the time dependent aspect of it, and also inelastic response. So once we have a proper material model, so we need to set up a governing differential equation, right? So this is to solve our like a boundary value problem. So that's it's ended up with a set of partial differential equation. Oftentimes it is non-linear because we work with this polymer that's typically undergo large deformation and experience a non-linear response. So at the end, what we also need to do is to be able to solve them, right? So we have a set of equation, we have a model, but in the end, we also need to be able to solve them. So we use a numerical approach, so either finite difference or finite element based approach to solve for our differential equation. So now, as an outline, I will just briefly, I guess, in all these categories, share with you what we have done in terms of the approach to the modeling and simulation. So the first is I'll discuss how we ended up with modeling nonlinear viscoelastic response of polymer when it's exposed to temperature and mechanical stimuli. And the second aspect is within the same idea, but now we are looking at the biodegradable polymer. And the next component, I will also share with you how we approach the modeling, the processing or cure of the epoxy material and also for the composite. And at the end, I will just show an example of capturing the response of this bilayer folding. Now, for the first example, so we work with polyoxymethylene. This is a POM polymer. POM is a thermoplastic polymer. So while our group has been working on the modeling and simulation, so this is a collaboration with Dr. Berer from Polymer Center in Austria, where they have gave us all this experimental data for us to play with. Just to give a background about what POM is. So POM is actually a thermoplastic polymer, and it is semi-crystalline. So when you look at in the polymer chart, so this is like we have like a different kind of polymer depending on their performance and resistance to temperature, right? So this is from the lower charts where it can resist relatively low temperature to the high performance polymer where it can stand about like 400 Celsius. But of course, when we say about high performance polymer, 400 Celsius, when you look at this, it's much less than what metal and ceramic can actually sustain, right? So, but the advantage of polymer is relatively cheap and also it's easy to process. Like I mentioned earlier, so we can really tailor the properties to some extent within certain range and customize the properties through the polymer blending and also through the processing. So that's what the advantage of the polymer. So make it easy for us to do all this mix and match just to see what kind of a different behavior or performance that we could get, right? So while POM is actually here, so it could sustain about like 150 Celsius. It's not too high, but it's good enough. So it has a good mechanical characteristic. So typically it's being used in automotive industry for like a fuel housing system or gears component. The processing also like a typical polymer processing, like for example, injection molding or compression molding. So when you look at the commercial name, it can come of various of names. So I'm just gonna give two examples of them, like a Delrin and Celcon. That's the commercial name of this POM polymer. So now, for being a thermoplastic polymer, so POM specifically is a semi-crystalline polymer, right? So now when we look at the mechanical response of this polymer, so first I'm just showing you this charts. So when you look at this is a typical stress and strain response when we test polymer. So this is under tension. So when we look at the microstructure of this polymer, the starting point, it has all this random long chain, right? So as you stretch them, this random long chain try to realign, right, towards a certain loading direction. So now during this realignment, as you can see, we can really draw them or stretch them to relatively large strain. So now when it's all aligned, all this polymer network all aligned in one direction, when you keep on loading it, we see stiffening, right? Because all this fiber add the stiffness to the overall response. Until at some point we see all this polymer network breaks, there where is actually our fracture point. Now, what approach we did actually to capture the response of this thermoplastic polymer? So what we are doing is we're taking the idea of these microstructural changes. So when you look at this cartoon, the microscopic stress strain, what we said is the following. So in its initial condition, so the polymer has this random network. So when we have this random network, the polymer has its associated physical properties. So this is what we call original microstructure. So now where if we only looking at the elastic property, you will see I have this elastic stiffness tensor associated with all this initial microstructure, or where the network is still randomly oriented. As we stretch them, as I mentioned earlier, so there is a microstructural changes, while at the end point, so they are all already aligned toward a certain direction, right? So now we also said, okay, if the polymer network has been all aligned, so it has its own associated the physical properties. So now when we said, okay, here is the final microstructure, it has an associated elastic modulus. So we call it like CF, this is for the final, C naught is for the initial or original. What happened is somewhere in between. So now during the transition from original to final microstructure, we said, oh, the material has actually a combined microstructure of this random and aligned fiber. So this, you can think of it as a composite with a combination of a different microstructure, right? So now for that, we said, okay, what is the material, the physical properties? So they would have a combination of the physical property of this original network and the final network. Now, how we link them together through what we call this internal state variable, we call it alpha. Alpha is the percent or volume fraction of this newly network or final network that is being formed during the loading. So one thing that I try to also point it out here, when we look at the microstructural changes, so when you load this and at some point there is a microstructural changes and you unload, right? You see this area that is associated with energy being dissipated. So that goes that when there is a microstructural changes, there is an energy being dissipated. In addition to this, when we talk about polymer, it's undergo viscoelastic behavior. So there is a delayed response. So in addition to all these microstructural changes, there is also the energy dissipation due to the viscous effect or viscoelastic effect of this material. So in our case, we model each microstructure as a viscoelastic material. Both this original and the final microstructure is viscoelastic. So then, of course, the combined overall response will be viscoelastic, right? Now, how we address this? I'm not going to go in detail with all of this equation, but the basic thing is we define the free energy. So in this case, we define the Gibbs free energy. That's account for initial microstructure and final microstructure, and also account for the viscoelastic effect. So in this case, we consider two networks. One network associated with energy storing capability. The other network is associated with both energy storing and dissipation capability, right? So as I mentioned earlier, while the idea of this microstructural changes and viscoelastic material is there is an energy dissipation. So here we quantify the rate of mechanical energy dissipation. So all of these derive from the thermodynamics principle. So this is, I'm just gonna show you like the final breakdown here. So we can quantify the rate of mechanical dissipation due to the delayed response or viscoelastic effect, and the mechanical rate of mechanical dissipation due to the microstructural changes, right? So now, through linking the stress and strain, so we satisfy compatibility and equilibrium equation. Well, the key point in deriving the model is picking the Gibbs potential. Well, how we pick this, of course, is based on the experimental data available to us, right? So, well, here we assume isotropic and homogeneous material. Just to show you an example, so inside this Gibbs potential here, we have material parameters. So this is, we call it AI and BI, which are temperature dependent. These are our material parameter. You can think of this as a compliance or associated with the modulus of the material. Now the other one, we also define what we call dissipation due to the delayed response. So we also have a material parameter here, which is also temperature dependent. So when you look at this material parameter, this is associated with the viscosity of the material. So there where we could actually have the viscoelastic response of this material, while we also looking at the microstructural changes. So when you look at this, I have this alpha, the parameter that I mentioned earlier, right? So this is what we have as the volume fraction of the new microstructure. So when alpha is 0, we only have original microstructure. When alpha is 1, so we only have the final microstructure. Somewhat in between, we have a combination, right? So from this Gibbs free energy, these are the final expression for our strain and its relation to stress, right? So this is the rate of the viscoelastic part, and this is the elastic component of strain. So now the question is how we define the microstructural changes or the state variable alpha. So in this case, we associated it with the strain, the current strain that is experienced like in the material due to external stimuli. So now, in terms of experimental data available to us, so there's been a several history of testing. So this is like a creep recovery at different stresses and temperature. By creep, meaning we load the specimen and up to certain load, and we keep it at a constant load. So then we would see the deformation or the strain continuously increase with time. So this is what we call a creep loading. And yeah, this is we do loading, unloading. We would be able to see hysteretic response. And we also ramp it until failure. So we also have data for tension and compression. Here we just look at the response of different POM polymers. So this is a difference due to the different molecular weight. So when you look at the overall qualitative response, they are more or less the same, but quantitatively there are some variations because of the difference in molecular weight. Now, just to compare how the model look like with the experiment. So these examples show the creep recovery under tension at two different isothermal temperature. The left side is at room temperature and the right side is at 80 Celsius. So now we have all these response for the three different POM. We call it Delrin 100, 500, and 900 at two different stress level. So the left side is low stress level, the other one is higher stress level. Now, the solid line is the response from the model, while the symbols are the response from the experiment. As you can see that the model can capture the experimental response quite well. So this is for the creep recovery. Now this is for the tension, quasi-static until failure, again, 4 different type of Delrin and at different temperature. Same thing, the solid line is for model and the symbols are for experiment. Now I also show you the loading, unloading. So this is loading and unloading response under tension. The at high temperature, 80 Celsius, while the bottom one is loading, unloading under compression. As you notice here, so we see the large area. So this is the amount of energy being dissipated, right? So while tension, we show larger energy dissipation compared to the compression. So this energy is dissipation partly due to microstructural changes and also due to the viscoelastic response. So now, as what you see here, the response of the material changes with temperature. And in addition, it's also show the energy being dissipated, right? So what we're gonna do actually next is, what if we do cyclic loading? So we continue this loading, unloading, and reloading, unloading, and continue under several cycles. So that would lead you to what we call like a cyclic or fatigue study. So this just to show you the simulation, how the fatigue or cyclic response look like. So this is at relatively low stress. This is at relatively high stress. Now, because of the dissipated mechanism, when we accumulate more and more cycle, right? So energy being dissipated, it's converted to heat. So that's what it would increase the temperature of the body. As the temperature of the body increase, it will affect the performance of the polymer. So now when we see all of this in the long run, so we would like to study or predict the fatigue failure of this material. But now we don't have the experimental data yet. So this, up to this point, is only simulation that we would observe. So when we look at like generate this in the structure, this is just a simple beam, right? So under loading, unloading, and reloading, unloading. So this is the tension region, and this is the compression region. When we look at like a 3 or 4 cycle, you already start seeing heating. So this is what we call hot spot, right? So this is the temperature distribution after 4 cycle. We start seeing like higher temperature. Now, when you continue like for a larger number of cycle, you'll see more and more energy being dissipated, and it would generate more and more heat. So that would increase the body temperature, right? So what's the consequence of this is that as the materials are very sensitive to the temperature, so this would also lead to what we call later on is instability. So this is just to show the simulation. So this when we allow the heat conduction, right? So this part is due to the dissipation as you keep on continue the cyclic loading. So we'll see temperature build up, right? So as the temperature continue increase, the polymer gets softened. So this we'll see through the simulation like a buckling or it lost a stability in this component. So while this response is like a temperature increase, so this will show you, this I'm just showing you the strain response of the strain component. So localized strain you will see at the later time, right? So as the polymer getting softer, it's undergo larger deformation. So that's where it's you start seeing all this failure or instability in the component. So now the lesson that we could take from here, we'll see the significant thermomechanical coupling, right? So at one time, the mechanical response of the polymer is very sensitive to temperature change. And on the other hand, when we talk about this polymer undergoing microstructural changes and also viscoelastic, it dissipates energy, where if we keep on continuing cycle this material, it generates heat, which in turn change the properties of the material. So this is what we call the coupling phenomena, right? So eventually, even though you think I did not apply any temperature, but the material would generate heat, and it's eventually would lead to structural failure. So this is an example of how we simulate or modeling a thermomechanical coupling problem. So then the next example, what I'm going to discuss is, with that knowledge, is actually we can also look at like a problem, like a different problem, but the knowledge can be transferred to predicting or understanding the response of biodegradable polymer, right? Just to give an idea about like what are the biodegradable polymers. So we have this synthetic polymer. We also have a natural polymer. So this synthetic polymer is polylactic acid or polyglycolic acid, and the combination of that. So that's what we call PLGA and so on. So these polymers are actually biocompatible and they are non-toxic. So that's what they found many application in biomedicine, right? So for example, in like a tissue scaffold, implant, or drug delivery. So these are the application. So we also find the application in packaging for biodegradable polymer. And you can also see in agriculture, right? So this is for the control release for agrochemical. So, well, what is the degradation process? Why we call it biodegradable? So the degradation is through hydrolysis, so meaning it needs an aqueous environment. So it starts with the water diffused through the polymer body. So there is a reaction, right? So that induces scission, so meaning a breaking of this polymer chain. So the long polymer now is break into like smaller chain. And if this breaking continues, so it will lead to the formation of what we call water-soluble materials, right? So these water-soluble materials can diffuse out of the polymer body. This is where we call erosion. So during erosion, you would notice the polymer undergo loss of mass. While during the diffusion, you would notice that the polymer has a mass gain, right? And somewhat in between, there is the hydrolysis process. So here is like a simplified degradation mechanism. While actually the process of biodegradation can be much more complex than what's actually I'm saying here, right? Because the scission could be like random scission or end scission. There could also be an effect of autocatalysis. All of this add complexity to the degradation process, right? So not to mention also different type of polymer will induce a different water-soluble materials. So now how we approach this problem? So what we did, okay, so we need all these basic components. So start with the diffusion of water. So CF is the water concentration, right? And we also have this component in which the water consumption during the hydrolysis process. And some studies suggest that when you strain them and there is a mechanical loading, it's also alter the diffusion process. Then you can also include that component here, right? So now during hydrolysis, as the polymer chain is breaking into smaller and smaller chain, it's actually quantified through the molecular weight change. So the molecular weight decrease as the hydrolysis process continue. So while this decrease in molecular weight is, in our case, we look at the degradation. So the degradation stage is when we see, okay, how much now the current molecular weight compared to the initial molecular weight. Now, when there is an erosion, so this water-soluble material, we call it like CM, diffuse out of the polymer body. So we also incorporate another kinetic process. As for the polymer itself, this is a viscoelastic material, and the property changes as the polymer degrade because the molecular weight change. So we incorporate all of this inside this constitutive equation. Now, just to show the prediction, so this is the stress relaxation of PLLA fiber at different strain level. So we see this is for only 10 minutes test. The stress relaxing, again, the solid line are the model which can capture the experiment. And here is also the stress relaxation after different states or time of immersion or degradation. 0 meaning early time, and after 6 months and 9 months degradation, right? So now if we already have a model in mind, so the next step is for us just to play around. What if we have a stand structure? Then you include all the material property and parameter that you already calibrate. Then we want to see whether the stand design is reliable and to what extent we might need to change the design, right? So this just to show you that at the junction here, we might have faster degradation because it has higher stresses due to all this stress concentration. But what is missing in this model is actually we did not include the erosion. So when there is an erosion, the size and the geometry of this polymer should also change, right? So which I'm going to discuss in a minute. So this also just to show you another design of stand when we look at the cyclic loading. So when you do loading, unloading, because of the degradation and also of the viscoelastic effect, you would see the hoop strain here continuously increasing with time. At some point, you cannot keep on all this strain continuous increase, right? So at some point, it will undergo failure and breaking of this stand. So when we design, so we need to have a design criteria in terms of what is the load bearing ability and the limit design. So then we could do a proper design to avoid like a catastrophic failure. Now, how we model the shape and size change during the degradation. So we look at what we call the level set. So this is just to tell us where is the moving boundary, where is the boundary now, right? So this is phi here is the variable that tell us the body or the geometric component. When it is less than 0, we have a solid polymer. When this is greater than 0, it's all fluid environment. And when it is 0, is our boundary. So what we are doing is we're tracking the boundary, and what is the speed of this boundary change is related to actually the amount of water soluble material exists in the polymer. So this is how we actually track the changes in the size and the geometry during the erosion. Just to give an example, so this is the degradation in PLGA. So this is a disc, start with the polymer disc. So we look at the molecular weight. So here is experimental data is from von Bucher-Soda here, available in the literature. So as polymer degrades, the molecular weight decrease, right? So here the simulation, we try to capture how not only the molecular weight change, but also the size and the shape of this disc change as the polymer degrade. So it starts with relatively high molecular weight, it's about like more than 10,000. And when it's degrade, it has a relatively low value of molecular weight. And here is the same degradation, but this shows the fluid concentration in the polymer. So when degradation occurs, some of these polymers still dry enough, right? So it's not all of them was already wet. And here is the amount of water-soluble material that exists in the polymer as it degrades. So now we also want to see what if we have a perforated polymer, because when we use it in a scaffold, it's often in the porous domain, right? It's not going to be in the solid disc. As expected, when you have perforated, it degrades faster. But one thing, when you do have a perforated, so you might end up at the later stage, it's like this component break into pieces, because I guess the junction here would degrade away as the erosion take place. And here just to show you what if we have another shape, right? So because all this geometry, the initial geometry would affect the degradation process. So we just want to show, okay, how we can capture all of these size and geometry change. And in addition, we're also taking into account the molecular weight change and the hydrolysis process. So from those two studies, now within the same kind of a spectrum or the same kind of knowledge, we could also apply to understand the curing process in the polymer, right? So because all of those involve the temporal and spatial changes in the physical properties of the polymer. So just to give a background, just a bit small background on the polymer or epoxy curing, right? See, it's involve phase transformation from the liquid epoxy to the solid epoxy. Is often done at higher temperature to accelerate curing, although you can do it at lower temperature, but the cooling process, it takes longer. during this curing, actually the curing reaction it is an exothermic, so it would generate a significant amount of heat. So they would increase the body temperature. And also at the same time, during this solidification, there is a shrinkage. So we do have a competing effect between the expansion and also the shrinkage. That all of this process would affect the curing process in the polymer, where it can also generate like a thermal stress, where if we have excessive thermal stress, it might induce defect. This is what they call it, processing defects, which this is something that we want to control or we want to mitigate. Now, how to do this? Of course, we need to understand the entire processing factor and history of this polymer. Now, without going into detail, like I mentioned, how we capture it, the essential mechanics is like heat generation and conduction, because it's involved high temperature. So we do have it at a relatively high temperature. There is a conduction. And during this curing process, the heat being generated. Now, this curing process also depends on the temperature and the pressure, right? So when you change the pressure and temperature, it changes the curing rate reaction. By being viscoelastic, again, the property changes with the degree of curing and temperature, right? So when it's in the liquid stage, it's highly viscous. As it gets solidified, the polymer is harder, so the viscosity is actually decreasing. So all of these would affect the overall viscoelastic response of the polymer. Now we also incorporate the expansion and the shrinkage in capturing this epoxy curing. So we also account for the changes in the physical properties, right? So this is thermal conductivity, thermal expansion, and mechanical properties. And this is the shrinkage model, right? So all of this change from the liquid states to the solid states will also affect the overall curing response. So what I'm trying to show here is that when you change the temperature, right? So from low temperature to high temperature, as you can see here, high temperature, it can cure faster. So low temperature, even when you, for example, this is at 90 degrees, even after you wait like 400 minutes, it's not undergo fully cured, right? Another way also, we could also apply relatively low heating. So this is when you ramp the temperature 1 Celsius per minute compared to what we call isothermal curing. So you just heat it up often to the very high temperature without controlling the heating, right? So this will have all the different effect to the polymer curing. So here's, for example, so here we show curing at the isothermal 200 Celsius. The curing also involves applying pressure, which is 10 megapascal, and heating to cure temperature. Now I'm just showing you the variation in the, here what we want to show is non-uniform curing process. So we look at randomly pick like a different location. When you look at this degree of cure, right, they don't cure at the same time. So this variation, which actually give us a significant amount of stress, as you can see here, while the pressure is 10 megapascal, if there is no additional stress, it should stay on within this 10 megapascal. Because of this non-uniform curing, you'll see these changes in the stress as you heat it up. When it's cured, there is also shrinkage. So now when you bring it down to room temperature, right, so you'll see another changes in stress. And in the end, you'll see what we call the residual stress. When it is high enough, it might induce a defect or damage in the composite or in the polymer. One thing that I also mentioned, well, curing is exothermic, it generates heat, right? So now you said, okay, this is my cure temperature is 200, but because of this exothermic process, it can go much higher than that. So all of this will affect the response of the cured polymer. Just to show you how the space and times change. So this is just to show the contour of the temperature and stress, right? So in the beginning, the temperature is still increased. So we see expansion as the polymer become larger due to the expansion effect. As it cure, it shrink. Now at the final state, you see we have all this uniform room temperature after cool down. While we still see here the what we call residual stress, and also there is warping in this polymer due to the non-uniform shrinkage and non-uniform expansion. This is actually unwanted, I might say, right? So as much as possible, you don't want to have warping in the polymer sample. Just to compare, when we cure it at a different temperature or lower temperature, you can minimize all those effects. However, lower temperature, it might take longer for you to cure, right? So this just to show you the table. When we do it at room temperature, even after 1300 minutes, it's still not cured. So when we go with the higher temperature, it cures faster. But one thing though, when we compare this at 290 degrees, so the modulus is slightly lower at 200 because of the build up in the residual stress that would reduce the modulus of the polymer. So now one way, what if we do a slow heating? So with slow heating, so you look at the cure time, 60 minutes is not too bad. And we have a properly cured sample with relatively high modulus. So when you look at the slow heating, so it's more uniform curing when you see all this degree of curing at different location, right? So with more uniform curing, we minimize the effect of this residual. As you can see, we see some changes in the stress, and they're all fluctuating very close to the 10 megapascal pressure that we prescribe. At the end, the residual stress is actually very small, minimal, compared to the previous example that I gave you, right? So all of this has a consequence on the material response. Now, when we use this epoxy in the composite, the response will be complicated because of the existence of fiber. This is just to show just a simple microstructure when we cure the composite. So in the beginning, we see swelling because of the expansion due to heating. At the end, we see all this shrinkage. This would induce stresses in the material. That would also affect the moduli of the composite sample, right? So this is where we said, okay, be able to control the curing process is the key of having a good finish of the epoxy and the composite eventually. So with that, so my final example is actually how we want to capture the bilayers of the polymer folding, right? So the idea of this is for microfabrications, and I'm showing you these two articles, which I think is interesting article. So the first one is actually the combination bilayer out of polymer and gold. So the activation here is through voltage or electric field. Because of the difference, a significantly different response between the two layers, through the electric field activation, you can achieve all these folded shape, right? So, well, in the second example, this is bilayer of two different polymer with significantly different physical properties. Through the non-mechanical stimulus, for example, you can consider temperature, pH, or moisture, you can achieve a different folding shape, right? So this example is actually the polymer folding by Stoichkov. So where this folding is due to a moisture absorption, because in the bilayer, they have two different layer. One is hydrophilic polymer and the other is non-active polymer. So the key of this is actually we look at the interplay between the geometry, the material, and the properties, and of course the external stimuli, right? So the purpose is for microfabrication. When you have a very, very small scale, it's really difficult for us to generate a complex shape or complex geometry, right? So through the idea of this folding, you can achieve various complex geometry, but of course we need to know the interplay for all of these aspects. Just to give you a simple example of this bilayer. So we have the model, of course, constitutive model for the substrate. This is an inactive layer. And we also have a model for the active layer. Now, depending on the activation mechanism, in this example, we show with the electric field, right? So that's what we need the constitutive model for electric field. If you use a temperature or moisture, you might have a different constitutive model. So with all of these constitutive model you put together in the bilayer, right? So this is a very thin layer. So we use a shell element in order to capture this. So now we look at the response when we activate it with different electric field. So of course the response would really depend on the geometry, right, of this component. When we look at just a square geometry, so in the beginning it tend to create the dome shape, because in the minute you activate electric field, so there will be stretching uniformly across this plate, right? However, these plates need to achieve their stable state. So that's what at some point there is a snap, it goes to the cylindrical state, because this is actually the stable state which require a small amount of energy. So why that it cannot sustain the dome shape is because we start with the flat panel here, right? So in the Gaussian curvature of this flat panel is 0. So when we just apply electric field, right? So we tend to create a shape, but in order for us to create a dome shape, we cannot create a dome shape without stretching them. So now the only shape that can be created without stretching or cutting the sample is where they could have a zero Gaussian curvature, right? So because it starts with the flat panel with a zero Gaussian curvature, so that's what is ended up with this rolling state. Well, the same thing when we have a stripe, it's easier because of, again, the aspect ratio. So it's create immediately this folded pattern. And you also notice there is a warping here. So it's not that we can like clean folding. You see all this warping effect. So this is because when we try to activate it, there is also like the stretching in the lateral direction that would create all of this warping effect. So now you can also look at the different this. So this is when we look at the circular shape, you can have multi-stable components. So depending how you activate it, when you do slow or fast, right? So you can generate either the first stable configuration or maybe the second stable configuration. So this, again, the idea behind this is snap-through mechanism, where this plate need to find its stable condition, which require a minimum amount of energy. So, well, another aspect that we want to show, since we are dealing with polymer, it has all this delayed or time-dependent response, right? So you can also activate it, and if you hold them at a certain amplitude, with time, it could generate or continuous folding. So this is because of the delayed response due to the viscoelastic effect in the polymer. So with that, so I share with you, right? So in terms of how we model the polymer only from the constituent, so looking only the polymer response, and we can also bring this to the structural scale. So I give an example here in the bilayer folding. So all of this is actually require like the basic knowledge in the mechanics of polymer, including the nonlinear response, right, to achieve all of this response. So in the end, so I would like to also acknowledge the collaborators, both at Texas A&M and outside Texas A&M, and also former and current students who's actually working on these polymer projects. So with that, that's all I have, and thank you. So now I believe we open for questions.
All right, thank you very much, Professor Anastasia. That's very interesting talk. I just want to give one comment here. It's not a question, it's just we have also almost the same thing in my field, in robotics. We have such as compliant mechanisms. So making the robot, instead of using joints and rigid links, I'm working.
Okay.
So we use the whole materials, and the robot will move with the what you call as a mechanical stimuli, probably. So we call it as a compliant mechanisms. I'm not working on that area, but that I see that area is very interesting as you presented this morning.
Yeah, definitely. That's like the current. Probably that's maybe like what you call the current states of this robotic field. That's what I heard a lot about soft robotics application.
Yeah, soft robotics, but compliant mechanism is quite small because with the mechanical stimuli, with the temperature, so the displacement, what we call displacement, would be quite small.
Yeah, this is relatively a small size of device.
Exactly. Yeah. Right. That's very interesting talk. Now it's just in time. So I'm going to open for the question and answer session. We have one participant is raising hand. Committee, if you may help me for Mr. Rekso Warjoyo.
Oke, kedengeran suara saya?
Yes. Ya. Bisa, Pak.
Selamat malam, Bu Anas. Masih ingat saya? Saya yang di Bu Anas dengan Pak Sangriadi dan Bu Herlin.
Pak Sang, ya, aku ingat Pak Sang.
Maaf, saya bahasa Indonesia saja ya, mungkin lebih harap.
Silakan, Pak.
Wah, saya bangga sekali sama Bu Anas nih, walaupun saya cuma ngikut uji saja ya. Wah, kapan ke Bandung?
Biasanya sih saya tiap tahun pulang, Pak. Cuman ini berhubung COVID.
Hebat, salut.
Jadi ya tahun ini nggak pulang ke Indonesia.
Murid-muridnya Bu Herlin hebat-hebat.
Waktu 2 tahun lalu saya pulang ketemu Bu Herlin. Tapi pasangnya nggak ada.
Oke. Saya nggak mau banyak kasih komentar tentang bidangnya karena bukan bidang saya, tapi saya juga bercimpung dalam bahan bakar, tapi yang biodegradable, biofuel. Nah itu banyak masalah karena bahan bakar ingin stabil, sedangkan biodegradable ingin cepat berubah menjadi kembali ke alam ya.
Iya.
Nah itu sangat bertentangan. Jadi mungkin bukan pertanyaan sih, komentar itu bisa nggak ada teknik yang bisa membuat lebih lambat atau memperlambat biodegradable. Itu satu. Kemudian kedua, saya hanya ingin memberitahu anak saya juga alumni sipil. Anak buahnya Bu Herlin juga. Mungkin
angkatan berapa, Pak?
2008.
Oh, jauh.
Arka Reksawardoyo. Sekarang masih di PFL Lusan, baru selesai S3.
Oke.
Nanti bisa di-search Arka Reksawardoyo, dia akan postdoc di Stuttgart.
Oke.
Jadi bidangnya mungkin beda, tapi masih ada hubungannya dengan Bu Herlin. Jadi namanya adaptive structure.
Adaptive structure, oke.
Nanti mungkin bisa ketemu entah di mana lah. Ya, itu aja mungkin. Saya bangga sekali sama Bu Anas nih. Masih warga negara Indonesia, sudah Amerika.
Didikan Bu Herlin.
Ya, saya ingat sama Rani itu ya.
Oh ya, Rani.
Ya mungkin itu saja. Terima kasih. Saya masih mesti rapat lagi nih. Sukses terus. Terima kasih.
Terima kasih, Pak. Silakan Prof. Anastasia mengenai biodegradable fuel.
Well, sebenarnya kalau biodegradable yang saya tahu tentang polymer biodegradable, it is possible to control the degradation time, of course within certain time frame. For example, when we look at PLLA, it's relatively longer degradation. It could take years, like 12 months to 24 months. But it's because of the polymer component and the polymer chains and also the basic component. So that's why the degradation process is slower. But when we look at the PLGA, polylactic glycolic acid, the degradation time is a lot shorter. With PLGA, actually by varying the composition of lactic and glycolic, you can have the degradation change from like within days, week, 2 months. So within that time frame, we can control it. But then I'm not sure if we work with, there are also biodegradable metal, which are non-polymer. I'm not familiar with that, but I don't know to what extent that we can control the biodegradable for that material. But within polymer, to some extent, we can control. But of course, there is a range. You cannot say, oh, I want it to degrade for 5 years or 10 years. Maybe it's not possible. But for some polymer within a certain windows, we can do that through a different blending or copolymerization and through also different processing.
Okay, thank you. Saya harap itu menjawab. Saya lanjut ke pertanyaan selanjutnya.
Ya, terima kasih Bu Anas.
Sama-sama,
Pak. Itu kelihatannya penting sekali itu, karena bahan bakar itu sekarang cuma bisa 3 bulan ya, biodiesel dan sebagainya. Nah, itu jadi masalah besar. Jadi kalau bisa dikontrol setahun begitu mungkin alangkah baiknya begitu. Ya, mungkin itu mungkin topik buat Bu Anas buat berkarya di Indonesia.
Next topic ya.
Oke, mungkin terima kasih sudah merepotkan.
Ya, sama-sama Pak.
Next topic dan homework ya Bu ya.
Ya, homework.
Next questions from Bagus Alifah Hashim. Let me read the questions here. Hello, my name is Bagus Alifah Hashim, and he is interested in material engineering, especially for polymers and composites material. We know that polymer has a bond which hold the neighboring fibers by van der Waals force. So this force is categorized as the weak force, comparing with Young modulus of the fibrous polymer. Then his question is actually, can we actually recover the polymer structure after the van der Waals force breaks?
I'm not sure if, okay, you're talking about the bonding in between the fiber and the polymer?
Yeah, so he's talking actually about the van der Waals force. And he said that it is categorized as the weak force. So his question is actually how to recover the polymer structure after the van der Waals force breaks.
How to recover the polymer structure? I'm not sure if I understand what's the, I mean, how it's leading. Is it the interface between polymer and fiber, or just the polymer breaking in general?
I'm not sure here. I'm sorry, I cannot help you. Or probably this is more about the stretch fibrous polymers to its origin.
For the polymer, for the fiber.
Yes.
So, you're talking about the healing, or what is polymer healing? Well, we have not really looking at the healing. Some polymer can undergo healing, but the one we study, I don't think we ever seen the healing process in this polymer.
Is there any like van der Waals force in polymer?
Oh, there should be. Like if you look at the molecular, the basic building block, they would be there. But yeah, we did not really study in that molecular level.
All right.
So I don't know how much it is. So yeah.
Okay, so I'm trying to again here the next question still from Bagus Alifah Hashim. Is there any specific process to relink or recombine the stretch fibrous polymer to its original links? Is there
Are you talking about the molecular structure? For example, epoxy is cross-linking and some other polymer is governed by crystallization or amorphous network. Is it the question?
Yes.
So yeah, for example, when I look at the polymer processing is epoxy, right? So when you look at degree of cure is actually the amount of crosslink. So when it's in the liquid stage, there is no cross-linking. As it cures, it formed the cross-linking. So when you look at this, maybe I should go back to the equation. Just a second. So when we look at this, here it is. So this actually, the psi is a degree of cure, is actually also the amount of crosslink being formed, right? So you can look at like a percent crosslink. The idea when it's fully cured, so you expect to have 100% crosslink, but in reality, we never get 100%, but it's very high number of crosslink. So this is for epoxy, specifically for epoxy. For other polymer, the curing maybe by increase in crystallization, there will be a different mechanism.
So different materials will have different mechanisms of...
Yeah, different polymer will have a different macromolecular network.
Thank you. So we'll come back here to the participants who is raising his hand. There is Andi Kuswoyo. You can talk directly to the speaker and deliver your questions.
Okay, thank you for your hands. My name is Andi Kuswoyo, and I'm from the same unit, but I'm sorry I couldn't solve the video because the internet connection here is like that. Okay, my question is, actually I have several questions. The first question is, you talk about the rate dependent or time dependent analysis about the composite, right? And
I hardly can hear you. You're breaking off. Is it my?
Yeah, your voice is not that clear. Can you repeat again a bit slower?
Okay, maybe I will ask you in Indonesia. Okay.
Yeah, it's okay. It is just the voice is breaking off.
Begini, pertama mohon maaf, internet di tempat saya tidak bagus, jadi mungkin suaranya jadi putus-putus.
Ya, putus-putus.
Oke, pertanyaan pertama saya sebetulnya untuk tadi terkait dengan time dependent, Bu. Itu kan ada time dependent untuk komposit. Itu kan berarti hanya untuk termoplastik berarti kan ya. Untuk thermosetting menurut Ibu gimana gitu?
Yeah. So yes, thermoplastic and thermosetting has a different processing mechanism. So it will need a different different model. And of course, when it's cured with thermoplastic, if we have a crystalline phase, so we look at actually a degree of crystallinity. Well, specifically, I studied epoxy because when it's cured, it's decided by the degree of crosslink. So that's what we look at the crosslink effect. Yes, it's really depending on the polymer that is being studied.
Oke. Kemudian untuk yang kedua, ini kan yang tadi terkait dengan yang ini yang modeling epoxy curing. Pekerjaan ini kan berarti dilakukan secara numerik. Nah, bagaimana memvalidasi model numerik yang dibuat? Apakah ada eksperimentalnya? Kemudian apakah itu hasilnya dibandingkan dengan eksperimental?
So we can only, for example, to some extent, let me go here. So the problem is with when we do all this polymer curing. So here's, for example, the comparison between the model and the experiment, right? So a lot of time it's so difficult to collect the experimental data. So we can only, for example, looking at the degree of curing, in this case, through the heat generation, right? So then now we compare the solid line, again, the model and the symbol are from experiment with the different temperature. However, the challenge here, when we look at specifically like a variation, like, here maybe is clear, right? Yeah. So when we look at the non-uniform curing, so here variation in temperature, variation in stress, currently it's really difficult to experimentally detect all of these local effect. So we see this through simulation and overall behavior, we could maybe link it to what do we see in terms of a degree of cure. So that's, I think, the best we can do at this moment. But if we have an experimental tool or capability that can really tell us, so what is going on in a different location, how much stress occurring at certain location, that would be maybe helpful just to corroborate, okay, is this model really aiming in the right direction? So that's, I think, has been a challenge. And even with the temperature, we know that there will be temperature variation in the beginning, but can we really capture, okay, there will be high temperature at certain location while a bit lower at the different location? So this is, I think, yeah, in terms of experiment, there will be a challenge. Then, yeah, I'm not sure if we, for sure, I don't know how to do it, but if there is a way or someone has done it, this something, maybe I think we can look into it.
Oke. Nah, kemudian yang tadi kalau misalnya berdasarkan hasil simulasi itu kan misalnya ada suhu yang 30 derajat, bahkan tidak cure, bahkan ada waktu 1.300 menit atau lebih dari sekitar 20 jam, itu epoksi tidak kering. Tapi bagaimana kalau saya kita lihat?
So that's what I think realistically, so we generally don't cure at room temperature. This is like for a simulation you would see, right? So even at after a longer time, you don't really see is undergo like a fully cured. So, well, obviously there is a limit of time that where you want to wait for this or do the processing.
Betul.
Right? So that's what typically we don't really cure the epoxy at room temperature. If we do that, so usually we stop it, let's say after a day or two, that you don't really get what we call a good quality. It might get hardened, but it's not really cured in a sense that forming a crosslink.
Tapi bagaimana dengan proses Seri, Bu? Vacuum assisted resin infusion itu kan maksudnya tanpa temperatur.
Bisa diulang? What's the question?
Iya, maksudnya tadi kan ada proses Seri vacuum assisted resin infusion itu kan tanpa temperatur gitu.
All right. I'm sorry, I may have to move on to the next questions. So if you have more detailed questions, I believe Bu Anastasia bisa dihubungi ya.
Yeah.
We have more detailed questions because I have list of questions here. And it seems participants are very excited with your lecture. Oke, Mas, bila ada pertanyaan lebih detail, bisa kontak langsung dengan Profesor Anastasia. I will read for the next questions here from Pak Irfan. Pak Irfan Hidayat from Materials and Metallurgy. So the questions here is, so he is talking about moving boundary during the process. Professor Anastasia has presented about that. And he's asking about, are there other techniques? Is there any other techniques so that we can track the moving boundary?
Then using the level set?
Yeah, so the level set, he said the level set function has been used to track the moving boundary. Then he's asking, is there any other techniques for doing so?
Probably there is, but maybe I'm not familiar with.
And to the best of your knowledge, in comparison to other techniques, if not sure if you know, what is the level set function preferred over other techniques? I mean, what is...
Because what I see with this level set function is pretty straightforward, right? So we look at if you look at the kinetic of moving boundary, so P here is our domain. So this is the rate of its domain change. So when you see all this association, right? So this is really like a kinetic, you can think of it as a kinetic process. So when you look at this, the speed, how fast the boundary should change. So we can really associate this with the concentration of water-soluble material. So in this case, we call it as the monomer. So this is why we said, okay, with the level set, I think it's pretty easy to implement and straightforward. So we can include this within our finite element or finite difference approach. So this is the reason why we use the level set method for the moving boundary. Well, there might be some other technique or tools, but I'm not familiar with whatever other tools there. So that's what, okay, this is the technique I'm familiar with. So that's what we're using it. So if you said what is the advantage compared to other, I cannot answer that because I'm not familiar what other tools out there.
Yeah, but I can see that level set function is quite straightforward.
Yeah, it's very straightforward.
Why you are using it. All right, let me read the next question, then I'll go back to the raise hand. The next question here from Bu Yanurita Dwi Hapsari from Physics Department. She's asking, she says that interesting talk from you, Professor Anastasia. Then she's asking, do you include cross-linking in your viscoelastic model?
Well, so it depends. So when you talk about the polymer processing, so that's I did not specifically mention this, but here it is. So this actually the rate of curing psi here, this is actually indicate the amount of crosslink being formed. When it is initially 0, we don't really have a crosslink. At the fully cured, you have a highly crosslink or close to 1. So that's where we look at this epoxy because it's true cross-linking. But now when you ask about the other polymer that I present, for example, like a biodegradable or POM, it is a thermoplastic and semi-crystalline, so it has amorphous and crystalline components, so it's not through the cross-linking. So that's what we did not have any cross-linking embedded in that polymer.
And how do you think the cross-linking affect the viscoelasticity? What is your opinion about that?
Well, the idea of this cross-linking is formed like a bond, right? So when you stretch them or when you release it, so this, unless this is breaking, so that's where the polymer, you can stretch it to some extent, to a certain level. But now when you look at the viscoelasticity, the mechanism is due to the delayed response. The idea because the polymer has a long chain, right? So when you have all this long chain is entangled, now you try to load them, right? So it takes time until all this molecular network actually come together and react to external stimuli. So that's where you see there is a delay in response. So the simple way maybe you can think of, I don't know, like, for example, when you hold hand, there are 10 people, and from the edge, like probably I pull one, right? So until the last person feel all this movement, it takes a while, right? So because of the long chain. So this is how, in a simple way, maybe the polymer network would react. That's what you see the delay in the response. So whether it's specific to the crosslink or amorphous or crystalline or maybe any other macromolecular network, that's I think like a different mechanism. Because most polymer, you would see all this time-dependent response.
All right.
Yeah, what I'm saying is not directly related to the crosslink effect. Because when you see like rubber, just a simple rubber, highly crosslink. But just stretch unreinforced rubber, you don't really see significant time-dependent effect. Compared to other polymer, it might have some, but it's not that significant.
All right. And I believe that answers the questions. And now I'll go back to the raise hand. There is Pak Alif Wikarta. He is my colleague from mechanical engineering. Pak Alif Vikarta.
Ya.
Halo, Pak Alif.
Oke. Tes. Mohon izin pakai bahasa Indonesia aja ya.
Silakan Pak Alif.
Ya, boleh.
Prof. Anastasia, nama saya Alif. Ini saya temannya Latifah.
Oke, salam kenal.
Saya usianya lebih tua dari Bu Latifah, tapi kemampuannya lebih rendah dari Bu Latifah. Jadi, kebetulan kami di lab solid mekanik, Bu Anastasia. Di teknik mesin itu ada lab solid mekanik. Pak, risetnya nggak banyak tentang polimer, lebih ke hal yang lainnya. Namun saya kira jika suatu saat nanti Bu Anastasia ke Indonesia, kemudian mampir ke departemen kami, ke lab kami sangat senang sekali. Bu Latifah itu tahun lalu itu punya tamu dari Columbia University, kemudian datang ke departemen kami, kemudian ada juga kolega kami yang lain juga punya tamu dari Norway dan juga dari Kingfat apa gitu sih pakai FUPM. Jadi kami sangat senang sekali bisa berkolaborasi jika memungkinkan ya. Di
so mudah-mudahan tahun depan bebas dari COVID bisa travel.
Ya mudah-mudahan vaksinnya lancar dan tahun depan sudah nggak ada lagi
bebas
corona.
dari pandemik.
Kemudian yang berikutnya, saya curious aja Bu Anastasia, itu Ibu solve sendiri equation-nya itu, ya, atau depend on mahasiswa postgraduate Ibu, karena kan nggak mudah ya untuk mendidik mahasiswa punya kemampuan. Mungkin banyak orang punya kemampuan, tapi mau
It takes time to
teliti gitu menyelesaikan bersama diferensial itu kan parsial, apalagi ya itu kan nggak mudah ya. Itu saya kira Ibu punya kompetensi itu sejak dulu mungkin ya, sejak studi S2 S3. Tapi saya curious saja gimana caranya Ibu mendidik supaya mahasiswanya mau gitu ya, karena kami di sini kesulitan untuk mendapatkan hal seperti itu. Saya dulu sempatlah gini pakai complex variable method untuk menyelesaikan dislokasi pada composite materials. Ya theoretical, ya modeling gitu, tapi ya nggak lanjut gitu. Karena kalau saya sendiri yang ngerjakan ya saya nggak bisa ngerjakan yang lainnya. Jadi cari mahasiswa sendiri pun sulit. Karena gini, ini lanjut ke pertanyaan yang berikutnya, yaitu kawan-kawan mahasiswa di tempat kami itu lebih senang kalau lihat ini aplikasinya apa. Katakanlah Ibu punya kerjasama dengan apakah ini perusahaan software atau perusahaan yang lagi mau develop new business opportunity, kemudian melihat butuh modeling terhadap suatu polimer jenis baru, kemudian itu mungkin bisa juga Ibu explore, nanti Ibu ceritakan ke kami supaya lebih termotivasi gitu ya. Kira-kira itu pertanyaan dan beberapa informasi. Terima kasih.
Oke, siap. Terima kasih Pak Alif. So mudah-mudahan tahun depan bebas pandemi, jadi kita bisa ketemu langsung. So, nah untuk pertanyaan yang kedua, I think it's easier if I just answer in English this one.
Okay.
So it's not easy to find a student in general, people who are interested in doing theoretical and simulation, right? A lot of people would like to see simulation because in the end you see colorful picture. It's cool, nice. But what they didn't want to do is do the dirty work behind the scene where you have to do derivation and okay, I have this set of equation, but if I cannot solve it, you're not going to see colorful picture, right? So you should be willing to learn it. But of course, there are some students who's really interested in this kind of work, like solving all these equation analytically and really like to do numerics. So while I can only work with students who are interested in computational and theoretical, if they are not interested, they prefer doing experiment, generally it won't work. it is just not possible because you're not interested to start with, and there is no motivation in learning, because really a lot of things to learn, right? For every problem. For example, when I started my PhD with the viscoelastic polymer, that's it. And then we go with the micromechanics of composite. So I did not have any background like in terms of heat transfer, moisture diffusion, and so on. But with time, of course, I need to learn all of this. Like what is the heat transfer? What is the heat conduction? So now how all these two link together? It takes time to learn, only to understand the basic concept. Then moving to what are the model available out there? What are the model or the new thing that is not available, but maybe is necessary for us to solve the problem, right? So because I generally is really interested in the theoretical and computational aspect of it. So that's what I would invest time here. But on the other hand, I don't really like doing experiments. So that's what, if you ask me in terms of experiment, I don't know much about it. That's why we collaborate with a lot of experimentalists. It is a matter of interest. Yes, we could find students who are interested in that. It might not be easy, but once in a while you find them.
Yeah, I would say this is all our, I'm not say problem, this is all our task as a teacher.
Yeah.
To build motivations for the students. I can relate to you because I'm working a lot with, I'm not working on numerical, I'm working a lot with analytical and theoretical works. So it's true as what Pak Alif said, students want to see the applications, the colorful plots, as you said. But to generate all of that, we need to finish the dirty work behind that.
Yeah, so that's the thing. Otherwise, you just paint it. You can paint. You don't have to do.
Yeah, but I'm also curious. Do you somehow divide the task? Let's say the theoretical works focus for the PhD, and the experiments are for the student project for bachelor's. Do you divide
No,
it? Or?
it's not necessarily like that. We do have some undergraduate student or master student who's really interested in doing theoretical and computational work. We do have PhD students who's not interested or to do experiment. So I really think it's matter of personal interest. So I don't think like undergrad prefer this or graduate prefer that. But it's really a personal interest. That's my opinion.
You're right.
So yeah, it's not always easy to maybe engage to student doing all this detailed analytical calculation to start with. So maybe a lot of students when they are starting elementary, high school, they don't like mathematics. That might explain.
Yeah, that's right. All right. So as Pa Alif said, we do hope that next year, as the pandemic is over, we hope so. We may collaborate, especially Pa Alif. Pa Alif is from Solid Mechanics Lab. So we do hope that you can visit us, or in
I
reciprocal.
would love to. Yeah, definitely. I would love to.
Collaborate. All right, so I will read, I believe this is the last questions in the chat group. You may also take a look at it, Professor Anastasia. The last question here. Hi, Anas, I believe that's your nickname, probably.
Yes. Oh, I have a lot of friends from undergrad here.
All right. Hi, Anas, proud to hear your achievement. What do you think about to invent or create a new material? That's heavy. Having
That's heavy.
the chemical and mechanical properties of most material. I know this is a scope of our fellow chemical engineer, but it is interesting if you have an idea, the material to replace concrete for nuclear plant. All right, for better in thermal and mechanical properties. All right.
Well, that would be, I guess, a difficult question because I'm not a material scientist, right? So lot of time I work with material that is already out there, looking at the mechanics of it and application. So like I said, my interest is be able to have all this digital model, or you can think of like also virtual testing if this is to link to the experiment. So I don't have any expertise in generating new materials, but of course, you always have like a dream. If I could have a material that can do everything at once, but that might not be possible, or maybe material scientists know how to deal with it. But it's always when you gain one property, you might lose other properties, right? So there's always this, you cannot have all. That's what my opinion. So for example, we work with polymer. I like it because there's a large variety that you can control. When you look at it, even high temperature polymer can only sustain 400 Celsius. While when you look at ceramic or metal, it can go beyond 1,000 Celsius, right? So far, I don't see that we could have a polymer that could maybe sustain like what the ceramic can do. But of course, ceramic, you can go with maybe 2,000 Celsius, but it's heavy. Polymer, on the other hand, is lightweight and very cheap, right? So there is always a balance. Once you get something, you might lose something. But the question whether I would be able to generate the new material, well, yeah, that's probably the answer. The question maybe for material scientist.
Right. This is somehow very interesting questions. And we definitely will need collaborations, multidisciplinary.
Yeah, definitely, because you need someone who really know a lot about the basic building block of this material processing and synthesizing material, right? I don't have knowledge in that field.
Exactly. Thank you very much, Prof. Anastasia. I see there is no more questions and we are just right in time. There is a pop-up here telling me that you actually finished undergraduate in civil engineering. Is that
correct?
Right. So this is very interesting. Now you finally end up in the solid mechanics somehow. So you can collaborate with us probably in the future.
Yeah, definitely. Right, so because I see a lot of opportunities. So yeah, my background is in civil engineering, all the way actually, undergrad, master, and PhD. But the research has been really on the solid mechanics, starting with polymer. So when I start my PhD, I didn't have any clue about polymer or composite. So it takes time to learn. But once you learn, I see a lot of potential and opportunity going in that area. So that's why I'm staying in that area instead of maybe working on concrete.
Right. I understand. I can feel you. All right, we are right in time. I would like just to summarize our discussion today. So Professor Anastasia Muliana, she's a professor from Texas A&M University in the United States. She has delivered a speech about its very broad topics in terms of solid mechanics, from biomechanics, 3D print polymers for skull, time-dependent materials, thermoplastic polymers, viscoelasticity materials. Even though I have questions myself, I will email you next time. I'm just curious. And biodegradable polymers and also epoxy curing that she has delivered this morning. We finally come to the end of the lecture. I would like to thank you, the speaker, for willing to share her knowledge, very valuable for all of us. Thank you to the participants who are very excited and giving the questions. You may also ask directly to Professor Anastasia if you have more detailed questions or if you want to collaborate more in the future. I hope this lecture will give you and will enrich you will give you valuable knowledge and enrich you. And in the end, I'd like to say stay safe and healthy, and goodbye, everyone. I would hand over this to our MC, Mbak Bilkis.
Thank you so much, Dr. Latifah. Okay, everyone, please give a very warm applause using the clap button or your Zoom to our speaker and moderator today. Thank you so much, Professor Anastasia Muliana and also Dr. Latifah. Ladies and gentlemen, let's move to the next agenda. Is a certificate awarding to our valuable speaker, Professor Anastasia Muliana. Committee, could you please help me to share your screen? Okay. Hopefully these appreciations would always attach in your heart, Professor.
All right. Thank you.
Okay, thank you so much. So, ladies and gentlemen, let's capture our moment today by taking a group photo. So, I would like to invite all of you to just a while turn on your video so we can have a virtual group photo together. Committee, could you please help me to capture all of the participants today? Okay. I will make a countdown from 5 to 1. And please, ladies and gentlemen, give a your very best smile to the camera in front of you. Okay. 5, 4, 3, 2, 1. Say cheese. Okay, once again. 5, 4, 3, 2, 1. Smile. Okay, thank you so much. Thank you so much, everyone, for turning on your video. And before we finish our meeting today, we are from the committee would like to inform you a very exciting of virtual public lecture, people-to-people relationships. We haven't give you the certificate anymore, so we replace it with the competitions. Mohon izin menggunakan bahasa Indonesia untuk informasi kompetisi diseminasi kegiatan virtual public lecture people-to-people engineering. Next. Ya, kami mengundang para peserta VPL P2P Engineering Field khusus untuk mahasiswa untuk mengikuti acara ini atau kompetisi ini, yang mana nanti bagi Bapak Ibu dan teman-teman mahasiswa yang sudah mengisi attendance link akan menerima link dari kami yang berisi rekaman dan juga materi dari VPL pada pagi hari ini. Kemudian peserta jika ingin mengikuti kegiatan ini harus memposting ulang, meretweet atau menyampaikan VPL di media sosial atau mengadakan workshop lokal di antara para mahasiswa atau siswa. Diperkenankan untuk melakukan aksi sosialisasi lebih dari 1 kali untuk mengumpulkan poin sebanyak-banyaknya. Dan peserta bisa menyerahkan dokumentasi setiap aksi diseminasi dalam PDF atau JPEG file melalui Google Form yang akan disediakan oleh ITS di dalam link tersebut. Kemudian, next slide. Ya, untuk mekanisme diseminasi, dokumentasi akan divalidasi dan harus dapat divalidasi oleh panitia nantinya jika memang terpilih menjadi pemenang. Kemudian peserta dengan poin tertinggi akan dipilih sebagai pemenang oleh panitia. Dan waktu pengumpulan dokumentasi sosialisasi adalah dimulai dari tanggal 28 September, ya ini adalah hari pertama VPL P2P Engineering, sampai tanggal 15 Januari. Jadi seri ke-12 bersama Profesor Anastasia ini adalah seri terakhir dari VPL P2P Engineering, tapi kami masih membuka kesempatan untuk mengikuti acara ini sampai 15 Januari 2021. Untuk hadiahnya adalah 2 beasiswa penuh untuk peserta yang mengikuti VPL P2P bidang engineering yang nantinya dapat mengikuti International Short Program di ITES pada tahun 2021 dan ini hanya untuk mahasiswa. Setelah itu, the next. Ya, ini adalah sistem penilaiannya. Jadi Bapak dan Ibu, teman-teman mahasiswa bisa melihat bagaimana sistem penilaian untuk kegiatan diseminasi ini. Untuk penjelasan lebih lengkapnya bisa dicek di halaman website dari ITS International Office. Next. Ya, knowledge is power, knowledge shared is power multiplied. Semoga dengan acara pada pagi hari ini kita masih bisa diberikan kesempatan untuk men-share apa-apa yang sudah kita pelajari bersama pada pagi hari ini bersama Profesor Anastasia Muliana, dan semoga itu bisa memberikan dampak yang positif dan multiplied untuk kemajuan Indonesia. Oke, baik, terima kasih banyak. Sekian adalah untuk competitions, P2P competitions, informasi P2P competitions dari kami committee. Baik, ladies and gentlemen, we have reached the end of our meeting today. Once again, we would like to express our great appreciations for our speaker today, Professor Anastasia Muliana, our moderator, Dr. Latifah, and all participants. We do hope everyone enjoy an insightful and joyful virtual public lecture this morning. And we also want to inform you that this is the end of the virtual public lecture P2P relationships in engineering field series 2020. And we hope to see you again in other P2P program in 2021. Okay, from the deepest of our heart, we do apologize for mistakes in presenting this event. All the committees deliver the best luck for all of you. Thank you very much and wish you a wonderful day. Bye-bye. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih.
Terima kasih.
Anas, terima kasih.
Terima kasih, Mbak. Sampai ketemu.
Terima kasih, Bu Ana.
Sama-sama.
Semoga
Terima kasih, Prof.
kolaborasi ya.
Terima kasih, Bu Latifah.
Ya, Pak.